Ladies and gentlemen, it's an honor to have this opportunity to present our demo paper. The paper is titled UP Miner, a utility pattern mining toolbox. The content of this demo includes the motivation for developing the toolbox, basic concepts of high utility pattern mining, and its emerging applications, the system architecture of the toolbox, and demonstration of the system. The main motivation for developing this toolbox is that utility pattern mining has received extensive attention in recent years due to its wide range of applications. However, there exists not yet a toolbox for utility pattern mining so far. To address this issue, we proposed a first of its kind toolbox named UP Miner, Utility Pattern Miner, that provides various functions for utility pattern mining. The first question that may come to anyone's mind is, what is high utility pattern mining? One typical application of frequent item sets mining is to discover sets of items that are frequently purchased together by customers. However, in this real-life application, it may lose infrequent but valuable patterns and may present too many frequent but unprofitable patterns. Because the purchase quantities and unit profits of the items are not considered, therefore cannot find patterns having high profits. Example, high utility item sets. Let me introduce the technical terminologies and basic concepts of high utility item set mining. I'll use this database as an example. In the framework of high utility pattern mining, each item has a quantity. For example, A has a quantity of 1. Each item has a unit profit. For example, in the profit database, A has a unit profit of 5. The utility of an item in a transaction is the multiplication of its purchase quantity by its unit profit. For the sake of simplicity, we have combined these two databases to give the transformed transaction database. Each item in the transaction in this database is accompanied by its utility in that transaction. A is followed by 5, which means the utility of A is 5. The utility of an item set in a transaction is the sum of the utility of its items. For example, the utility of AD in the transaction 1 is the sum of utilities of A and D in transaction 1, which is 7. The utility of an item set in a database is the sum of utilities of the item sets in all the transactions. For example, AD appears in transactions 1 and 3. The utility of AD in these transactions are 7 and 17 respectively, which sums up to 24. An item set is called high utility item set, abbreviated as HUI, if its utility is no less than a user-specified minimum utility threshold. Otherwise, it is a low utility item set. For example, if the utility is set to 30, BD is a high utility. B, however, is a low utility. In the application of market basket analysis, the discovered patterns can be used for product promotion, cross-selling, and catalog design. Besides market basket analysis, high utility pattern mining is essential to a wide range of applications. With the development of IoT technologies and sensor networks such as smartphones, wireless networks, and GPS devices, information about users' location and payment records can be acquired and integrated. In such scenario, HUP mining technology can be used to discover valuable user behaviors in mobile environments. It can be used to discover associations between customers' purchase behaviors and location trajectories in mobile environments. Discovered patterns can be utilized for location-based advertisements, navigational services, location-based recommendation systems, and many other applications. In web mining, users' browsing and purchasing behaviors are recorded in a web transactional logs. In such data, a user's browsing time on a web page can be expressed as the internal utility of the web page, and each web page may have a different importance depending on user's preference, that is, external utility. Website managers can use high utility pattern mining technology to discover utility-based patterns such as high utility access patterns and high utility transactional patterns in web transactions. The mined results can be used for electronic commerce to improve website services, providing efficient access to related web pages. Navigational suggestions for The mined results can be used for electronic commerce to improve web services, providing efficient access to related web pages. Navigation suggestions for traversing web pages, and improve the design of web pages, amongst others. An important application of high utility pattern mining in biomedicine is gene expression data analysis. In gene expression data, each row represents a set of genes and their expression levels, that is, internal utility, under an experimental condition. Furthermore, each gene has a degree of importance for biological processes, that is, external utility. The mined results can help medical researchers to develop new drugs for the treatment of diseases. Although high utility pattern mining is essential to many applications, existing softwares have not yet considered the concept of high utility mining. To address this issue, we propose the first toolbox called UP Miner for high utility pattern mining. The systems architecture of the toolbox is shown in this. It takes three kinds of utility-based databases, example, transactional databases, complex event sequences, and sequence databases into account, and comprehensively offers 6 technologies for mining different types of high utility patterns. It offers a user-friendly graphical interface, a utility-based data processing model, and a visualization model to users. Thus, users can use the system to easily access, process, analyze, and visualize utility-based data without complicated manipulations. It integrates over 21 implementations of efficient algorithms, including UP growth, CHUD, TKU, UP span, and many other state-of-the-art algorithms. The UP growth algorithm was published in CKDD 2010. The motivation is that previous approaches incur the problem of producing a large number of candidates for HUIs. Such a large number of candidates degrades the mining performance in terms of execution time and memory consumption. To address this problem, UP growth is proposed to efficiently discover HUIs with effective strategies for pruning candidates and search space. Experimental results shows that UP growth produces much fewer candidates than one of the state-of-the-art algorithm called IHUP, and is much faster than IHUP over 10,000 times on some types of datasets. I will now switch over to do the first demo of the toolbox using the UP growth algorithm. We first introduce the input data formats. The first part of the record represents items in the transaction. The middle part represents the total utilities of these items, while the last part represents the utility of individual items from the transaction. For this demo, we first choose the algorithm, in this case UP growth. Then we provide the input path of the database. Then we provide the output path for discovered patterns. And then we set the minimum utility threshold. Now we run the algorithm. This section shows the execution time and memory consumption of the algorithm. Now we take a look at the output. Each record in the output file represents information of a discovered item set. The first part represents the discovered item set. The middle part represents its utility, while the third part represents its relative utility. The CHUD algorithm is published in TKDE 2015. The motivation is that existing HUI mining methods may present too many HUIs, which degrades the performance of the mining task, because the more patterns are generated, the more computational costs are required. To address these problems, the CHUD algorithm is proposed to efficiently discover closed clause HUIs in databases. Experimental results shows that CHUD achieves a significant reductions, for example over 700 times, in terms of number of extracted patterns. Besides, it's also faster than UP. The data format for CHUD is the same as UP growth. First, we choose the algorithm. Then, we choose the input database. Then, we provide the output path for the discovered patterns. Then we provide the minimum utility and run the algorithm. Again, we see the execution time and the memory consumption of the algorithm. The information of the discovered patterns are stored in the output file. The TKU algorithm is published in TKDE 2015. The motivation is that it's not easy for users to set an appropriate minimal utility threshold. A too high threshold will result in few or no HUIs, whilst a too small threshold will lead to the generation of a large number of HUIs. To address this problem, TKU is proposed to efficiently discover top K HUIs without setting minimum utility threshold, where K is the number of HUIs that users want to find. Experimental results shows that TKU has good performance, and it serves as a good solution to the new problem of top K HUI. Again, we choose the algorithm. And then we import the database. The output path, and we set K. We use 3 in this instance, and we run the algorithm. This part shows the running time and the memory usage of the algorithm. The discovered patterns are stored in the output file. The related resources are made public on the web, which includes Toolbox, source code, benchmark datasets, utility-based data generators, and users' manuals. Thanks for your time. For more details about the Toolbox, you are welcome to contact Professor Vincent Sen.